Welcome to today's class on functional analysis. Today we discuss some examples of discontinuous linear maps. So we consider the first example. Let x equal to c prime 0 1, the space of all continuously differentiable scalar valued functions on 0 1, and y equal to c0 1, the space of all continuous scalar valued functions on 0 1. Consider x with supremum norm and y with subnorm. Define f from x to y by f of x equal to x prime, the derivative of x. Then f is linear, since differentiation is linear, but f is not continuous. For which let xn of t is equal to t raised to n, t belongs to 0 1. Then we have subnorm of xn of t. This is equal to subnorm of t raised to n, that is equal to 1, since t belongs to 0 1, closed interval 0 1. Now we have f of xn is equal to d by dt of xn of t. So this is n t raised to n minus 1. Therefore, the norm of f of xn of t, subnorm of f of xn of t is equal to subnorm of n t raised to n minus 1 that is equal to n, since t belongs to closed interval 0 1. That is subnorm of f of x1 equal to 1, that is equal to subnorm of x1, and subnorm of f of xn, this is equal to n, which is greater than 1, that is equal to subnorm of xn for n equal to 2, 3, etc. That is subnorm of f of xn greater than subnorm of xn for n equal to 2, 3, etc. which violates the condition that f is continuous if and only if norm of f of x less than or equal to alpha times norm x for all x in x and for some alpha greater than 0. Therefore, f from x to y where x is equal to dash c prime 0 1, y is equal to c 0 1 with the subnorm defined by f of x, this is equal to x prime, is not continuous. In this example, we have zero space of f is the set of all constant functions on 0, 1. Which is closed in X, and a range space of F equal to Y, which is infinite dimensional. Therefore, we cannot drop the assumption of finite dimensionality of R of F in the previous corollary. Now we discuss example 2. Define F from X to K by F of X equal to X prime of 1 for X in X, where X is C prime of 0, 1. Then the linear functional, then you know that F is linear, then the linear functional F is not continuous. So here we prove that zero space of F is not closed. Zero space of F is a set of all X in X such that X prime of 1 equal to 0 is not closed. Here the range of F is finite dimensional. Since F is from X to K and K is of finite dimension, therefore by 6.4 we get F is not continuous. So we prove that zero space of F is not closed. Consider Zn of t equal to t minus t raised to n by n, t belongs to 0, 1. Then Zn converges to t in X. We have xn of t is equal to t raised to n. Therefore, x1 of t is equal to t, that is equal to x1, defined as x1. That is, Zn converges to x1 in X. So we have Zn of t is equal to t minus t raised to n by n. Therefore, Zn prime of t is equal to 1 minus 1 by n into n t raised to n minus 1. Therefore, Zn prime of t is equal to 1 minus t raised to n minus 1. Therefore, Zn prime of 1 equal to 1 minus 1 raised to n minus 1, that is a 0. Therefore, Zn of t belongs to zero space of F. How zero space of F is set of all X in X such that X prime of 1 equal to 0. And we have, since Zn of t converges to t, that is equal to x1, and x1 prime of t is 1 and therefore x1 prime of 1 is 1. This is not equal to 0. Therefore x1 does not belongs to 0 space of f. Therefore 0 space of f is not closed. Since Zn belongs to 0 space of f, Zn converges to x1 and x1 does not belongs to 0 space of f, does not contain its limit point. Z of f does not contain its limit point. Therefore by 6.4 f is not continuous. A linear map on X may be continuous with respect to one norm on X, but discontinuous with respect to another norm. We can illustrate this using an example. Let x is equal to c naught naught. Consider the linear map f naught from x to k defined by f naught of x is equal to x of 1 plus x of 2 plus etc., where x belongs to x. Then f is continuous with respect to one norm on X, since modulus of f naught of x is equal to modulus of x of 1 plus x of 2 plus etc. So this is less than or equal to modulus of x of 1 plus modulus of x of 2 plus etc. So this is equal to sigma j is equal to 1 to infinity modulus of x of j. So this is one norm of x. That is modulus of f naught of x less than or equal to one norm of x. Therefore f naught is continuous. F naught is discontinuous with respect to two norm on x, since for xn equal to 1, 1 by 2, 1 by 3, etc., 1 by n, 0, 0, etc. in C naught naught, we have two norm of xn square, that is equal to sigma j is equal to 1 to n 1 by j square. So this is less than or equal to sigma j is equal to 1 to infinity 1 by j square. That is equal to pi square by 6. While f naught of xn, this is equal to sigma j is equal to 1 to n 1 by j. This tends to infinity as n tends to infinity. That is, f naught is not continuous on x with respect to two norm. Here we cannot say that modulus of f of xn is less than or equal to norm 2 norm of xn square. Now we have another example. Consider the linear map f1 from x to k defined by f1 of x is equal to sigma j is equal to 1 to infinity x of j divided by j for x in x. f1 is continuous with respect to 2 norm on x, but f1 is discontinuous with respect to subnorm on x. f1 is continuous with respect to 2 norm on x since we have modulus of f1 of x. This is equal to modulus of sigma j is equal to 1 to infinity x of j divided by j less than or equal to sigma j is equal to 1 to infinity modulus of x of j divided by j. So by Holder's inequality, this is less than or equal to sigma j is equal to 1 to infinity 1 by j square the whole raised to 1 by 2 into sigma j is equal to 1 to infinity modulus of x of j the whole square the whole raised to 1 by 2. That is modulus of f1 of x less than or equal to some alpha times norm 2 norm of x. This is 2 norm of x and you take alpha to be this sum. Therefore f1 is continuous with respect to 2 norm on x. Now we prove f1 is discontinuous with respect to subnorm on x, for which you let xn equal to 1 1 etc 1 0 0 etc in x equal to c naught naught. Here 1 appears n times. Subnorm of xn equal to 1 while f1 of xn equal to, by definition it is sigma j is equal to 1 to infinity x of j by j. So this is equal to sigma j is equal to 1 to infinity x of j by j. So this is equal to 1 plus 1 by 2 plus 1 by 3 plus etc plus 1 by n plus 0 plus 0 plus etc. So this is equal to sigma j is equal to 1 to n 1 by j, and this tends to infinity as n tends to infinity. That is, we cannot write modulus of f1 of xn is less than or equal to some alpha times norm xn. Therefore f1 is not continuous with respect to subnorm. That's all for the day.